Hello, welcome back to Control Systems lectures. So far, we have shown how two essential conditions must be fulfilled by a point S to lie on the root locus. These are the angle criterion and the magnitude condition. In this lecture, we will now provide some rules that will enable us to sketch the root locus that will give us an intuitive insight into the behavior of a control system. First, let us review the properties we have already discussed. The angle condition, represented by equation 8.12, which is the same as equation 8.7, indicates that given the poles and zeros of the open loop transfer function, a point in the S-plane is on the root locus for a particular value of gain k, if the angles of the zeros minus the angles of the poles all drawn to the selected point on the S-plane add up to 2k plus 1 multiplied by 180 degrees. The gain k at this point that has fulfilled the angle criterion is found by dividing the product of the pole length by the product of the zeros length, as given by equation 8.13, also represented by equation 8.11. Let us now give some general rules for plotting the root locus. The first is the number of branches of the root locus. Recall the example of the second order control system in lecture 802. I have reproduced it here. You can observe that there are two branches, the blue branch and the green branch. A branch is defined as the path that one pole traverses, which means that there will be one branch for each closed loop pole. The first rule, therefore, is the number of branches of the root locus equals the number of the closed loop poles. In other words, the order of the characteristic equation yields the number of branches of the locus. Like we have seen that the second order system yielded 2 branches and the first order system had 1 branch. The next rule is that the root locus is symmetrical about the real axis. Again, if you consider the second order control system example, you will see that the rule is obeyed. The next rule is the real axis segment rule. This rule states on the real axis, for k greater than 0, the root locus exists to the left of odd number of real axis finite open loop poles and or finite open loop zeros. The fourth rule provides the starting and the ending point of the root locus. The root locus begins at finite and infinite poles and ends at the finite or infinite zeros of the open loop transfer function of the system. For example, for this system, the open loop transfer function is k over s plus 10. This means that the path of the root locus will begin at s equals to 0 and s equals to minus 10. And since there is no zeros, which would have been finite ending point, the two loci will terminate at infinity, just as the root locus plot indicates. The last rule requires a little more explanation. The behavior of loci at infinity and the determination of the asymptotes as the poles approach infinity is determined from the following fact. The angle of the point s minus p subscript I and s minus z subscript I becomes approximately the angle of s. Therefore, the angle criterion becomes equation 8.15, and this will yield equation 8.16. The angles of the asymptotes that guide the direction of the root locus are therefore determined by equation 8.17, and the number of distinct asymptotes is given by n minus m, that is the number of poles minus the number of zeros. We can also determine where the asymptotes intersect the real axis. This is given by equation 8.18, which is simplified to equation 8.19. And finally, we also need to find out when the root locus breaks away from the real axis and where it breaks in again. Along the real axis, S is equals to sigma minus J0. Therefore, to find the maximum and minimum values of the gain K will correspond to the breakaway and break-in points respectively. Hence, equation 8.20 will be used. These rules will be used in an example to demonstrate their application. Let us summarize the rules for sketching the root locus for a higher order control system. 1. Number of loci is equals to the order of the characteristic polynomial. 2. Symmetry. The root locus is always symmetrical about the real axis. And 3. Real axis segment. For k greater than 0 along the real axis, a root locus exists to the left of an odd number of real axis finite open loop poles and or finite open loop zeros. And point 4, starting and ending points of the loci. Each locus starts at an pole and terminates at a 0. Note that the poles are indicated by X and the zeros are indicated by 0. However, there are usually more X than O's, therefore the remaining loci will terminate along asymptotes at infinity. Point 5. Determine the asymptotes as the poles approaches infinity. And 6. Determine the breakaway and break-in points of the loci along the real axis. I will use this illustrative example to explain the rules during our contact session. Thank you for listening.